Hello everybody, welcome to this presentation, and in this presentation we're going to be talking about the generalized I/O model on Linux. Now, the generalized model is very important to all other concepts when you're developing firmware in Linux and when you're generally just programming applications in Linux. And knowing how to use the file functions really affects everything else you do on Linux, because everything is a file. And this is one of the first things that I learned about Linux, and I thought it made a lot of sense when I got first introduced to Linux in the early 2000s, is that everything was a file, and it was just really simple to understand, and it's extremely powerful. So in this presentation, we're going to be looking at opening files and the different flags we can use when we open files. And we're also going to be looking into reading and writing data and how we can guarantee data integrity when we write data to disk files. And we're also going to be looking at when the closing of a file can fail, and a few more details on navigating files, seeking to different positions in the file, and then also a brief look at the generalized interface for anything that doesn't fit into this model of I/O input and output using files. I'm Martin Schroeder, and I'm an embedded systems consultant. I build embedded systems, so let's get started. So we're going to get started by a small overview of the file model. We're going to be dealing with file descriptors. A file descriptor is a small integer that Linux maintains for the process, which signifies the file that the index of the file that we are interacting with. And this file descriptor can be pointing, like multiple different file descriptors can be pointing to the same file. You can have multiple processes pointing to the same file, which is the file structure in the kernel. But for each process, we can also have multiple file descriptors pointing to the same file in the same process. And we're going to talk about that in a different presentation. Because that's a little bit outside of the basic usage of files. But the important thing to know here is that every file that an application opens and interacts with, which also includes every device and every terminal, every queue, any socket that the system interacts with, when you interact with network connections, because everything behaves exactly like a file. And so we have a generalized interface to index into those files that an application is using by the use of a file descriptor. And this applies to sockets, pipes, terminals, as I mentioned, FIFOs, devices, and also normal files. We have default descriptors, which are available to every application that is started, every process that you start in Linux, which are the standard input, standard output, and the standard error output. And they have fixed IDs, so they have an ID 0, 1, and 2. And all of these, the standard names are defined in the UniSTD file, which we can include into our C application. And we can use the same operations to interface with all devices in Linux. So this is really a generalized input and output model. And this allows us to reuse a lot of concepts for all types of devices. For example, internal kernel caching of data is the same regardless of what device you're interacting with. So we're going to start with opening a file, and for this we use a system call called open, and this call opens a file and it returns a file descriptor, which we can then use to read and write to the file and interact with the file. Now it's important to know that the file structure is maintained in the Linux kernel, so it's not accessible directly to the user application. It is stored in the kernel, and the way you interact with that structure is by using this file descriptor, which you pass to the system calls, which execute in the kernel space. So whenever we want to do anything to a file, we use the integer file descriptor, and we pass that file descriptor to system calls, which then modify the internal file structure. If the path name is a symbolic link, symbolic links are supported by most, by all Linux file systems. They're not supported by the old FAT file systems. At least they don't work the same way. But on Linux, a symbolic link is basically a link to a file, and we can open it just like we were opening a file. So from the application point of view, it doesn't really matter if it's a symbolic link. If the path name is a symbolic link, then it is dereferenced, which means that we are opening the file that it's pointing to. On error, open call returns -1 and sets the global variable error node to the error, which signifies whatever went wrong. We're gonna go over the errors a bit later in this presentation. For now, we'll just keep it simple and just look at the overview of the open call. We can specify different flags when opening a file. The basic flags are access mode flags, which are read-only, write-only, or read-write. Now, obviously, you need to have a permission in the file system in order to be able to open the file, whether it's read-only, read-write, or writing a file. You need to have the permissions for the user who is running the application in order to be able to open a file with the given permissions. But when opening the file, we can specify if we want to open the file as read-only, write-only, or read-write. And the open call is guaranteed to use the lowest available file descriptor, which means we can do things like, for example, closing the std out file number, which we discuss here. Std out is number 1. And if we then open a file and specify a path name, like for example we open a regular file, then we are guaranteed to get the file descriptor, which will be 1 in this case, because that's the first available file descriptor. Now this is mostly like a side effect, but it's good to know that this is guaranteed by the system. When we want to reopen file descriptors, we want to when we want to point the file descriptors to some other place, like for example, if we want to send the standard output to a socket, or if we want to send it to a regular file, we can use the duplication dup2, and we can use the fcntl file control functions in order to achieve that. And this is just basically a good to know basis that we get the lowest file descriptor. We can have more control over this using the specific system calls, and it also makes the application easier to read. But if you ever see this in an application where the application just closes a file descriptor and then reopens it using a path name, then you know that basically what it means to do is to reopen the same file descriptor if it's one of these lowest file descriptors in the application that are always there. Now, the second argument to the open call is the flags, and this is a very important argument. We're going to be discussing this for a while here, and the flags that you pass there are bitwise ORed together, and we have three types of flags. We have the access mode flags, which we already discussed here. It's read-only, write-only, or read-write. We have file creation flags, and we have file status flags. And let's discuss them in detail, because these are very important. These flags specify how you want to use the file and how the file behaves when you read and write to it. So let's look at first the file access mode flags, which we already briefly discussed before. But the important thing here to realize is that we can actually change these flags after we have opened the file. So we can use the file control function and use the fgetfl operation in order to get the flags, and we can use fsetfl operation to set the flags. And only one of these should ever be used at the same time. So we cannot, for example, specify read-write and read-only. It doesn't really make any sense. So because we are also bitwise ORing them, it will basically result into read-write. But just to avoid any kind of ambiguity, you use only one of these operations at any given time. Next, we have the file creation flags, and these flags basically specify how the file is created and how the file behaves when, for example, you fork the process, when you copy the program, when you copy the process that is running your program, and whether for example, the file descriptor should be closed or whether it should remain open and be available to the new process. So let's go over all of these in one by one, basically in this order. So oCreate determines whether you want to have the file created, and if path name doesn't exist, then the path name is created, and the mode, the last argument here that is passed to the open function, the mode argument, determines the permissions that are used for creating that file. We'll discuss that in a little bit more detail as we go along this presentation. So first of all, here is just an overview of the flags. We have the close exec, means that we want to close the file descriptor upon executing another process or executing another operation. Execute another application. We have O directory. It means that the call to open is going to fail if path name is not a directory. O exclusive is going to create a file exclusively. We'll discuss the implications of that a bit later here in the presentation. We have O large file. This is used on 32-bit systems to open large files. It's not used on 64-bit systems. O no CTTY means that the path name cannot become the controlled in terminal. We have O Nofollow. It means that we're not going to be following the symbolic links. If the file that we're trying to open is a symbolic link, we're not going to be following that symbolic link. We're just going to return an error. It's going to actually return e loop if the path is a symbolic link. We have also O truncate, which means that we want to reset the size of the file to 0 when we open the file. So let's look at each one of these in order, and we're going to start with. Let's see. Oh, we also have the status flags, and I'm gonna do a small overview here of the status flags as well. So we have the O append. It means that every single write that you do to the file is going to be appended at the end of the file, which is useful when you write log files, and it's very important to use O append because otherwise your writes are not going to be atomic, and you might get data corruption if you don't use O append. O Fsync means that we generate a signal. We tell the kernel to generate a signal whenever an I operation is possible to the file descriptor. We have O direct. It means that we want to bypass the kernel buffer cache and interact directly with the file on disk. We have DSync, and also the last one there is sync, and these two are related. They are used to have synchronized data integrity access or synchronized access to the data, which guarantees data integrity in terms of both the data of the file and also the metadata of the file. And these two work a little bit differently, but they basically achieve the same result when it comes to the contents of the file. That you get, you're guaranteed basically to have the data written to the hardware, whether it be disk or some other hardware. It's guaranteed to be written to the hardware after the call to the write system call returns. No A time means that we don't want to update the access time of the file. And this is useful if you're doing a lot of backups and you need to access a lot of files and do so quickly. When you set this option, you're basically avoiding the extra write operations which are used to update the time. So your copy operation happens a lot quicker when you do that. Non-block basically means opening in non-blocking mode, and this is useful if you're opening a queue, for example. Because in that situation, the call to open can actually hang, and it will hang in depth, or not hang, but more the correct expression here is it's going to sleep and wait until the queue is ready to be opened. But that can essentially put the program to sleep for an indefinite amount of time. So if you use non-block, you're always guaranteed to have the call to open return if the opening of the file is not possible at that particular moment in time. So the first flag we're going to discuss is the Append, and this flag is used for writes to a file. When we open a file using this flag, we basically are telling the system to append every single write at the end of the file. Now, if we don't use Append, what we need to do when we write to the end of a log file is to seek to the end of the log file first. So we will execute lseek, and then we want to write to the end of the log file. Now, this is a problematic thing because log files can be updated by multiple processes, especially if you have a web server which has multiple instances of the process running, and you don't want to have multiple processes called seek and write. Because that will generate data races. You will have one process called seek and another process write the data, and then you will overwrite the same data from another process that calls write again. So to avoid that, we have the Append flag in order to do this operation atomically. So when we provide the Append, then all writes automatically seek to the end first, and then write the data at the end of the file, which guarantees data integrity when we have multiple processes writing to the end of the same file. Now, important thing to know here is that not all file systems support Append, and if they don't support Append, then the system is not going to use that functionality, and you will end up basically with the data corruption that would occur if you don't use Append and just use seek and write. So all Linux file systems support this, but important to look whether the file system supports this or not. For example, network NFS file systems, they don't support Append, and whenever you're going to use Append, just make sure that you know that the file system supports atomic writes to the file system. Now, next on the list, we have option for asynchronous opening of a file. Now, this is only available on certain types of files, like sockets, pipes, queues, and iNotify descriptors. I'm not going to be discussing iNotify descriptors in this presentation, but they're basically used to notify the application of changes to regular files. But sockets and pipes and FIFOs are typical file descriptors that with which it is useful to use Fsync. And on Linux, we use the fcntl call to set the flag. When we pass it to open, it actually has no effect because we need to specify the signal handler for SIG.io before we set the OSSync for a file descriptor. If we want to sort of use the signal as is. So the kernel will send the SIG.io to the process whenever there is IO, whenever the process can do IO on any of the file descriptors. And if we don't register the signal handler for that signal, then by default the application will exit. So it's important to set this to actually set the signal handler before we enable a sync option on the file descriptor, on any file descriptor. Now, when we use async, then our performance scales according to the number of IO requests rather than the number of descriptors to be monitored. And this is why the asynchronous model has been used with such success in systems like Node.js, because you scale based on the number of IO requests and not the number of open sockets. So if you don't use async, then the more connections you have to the server, the more resources are used to, or the more time is used to monitor those sockets, and you quickly run out of resources to be able to do that. If you use the asynchronous option, then you scale according to the number of IO operations. So the more data is being transferred, the more work you need to do. But it doesn't really matter how many sockets you have, because the kernel keeps track of who needs to be notified whenever data is available on a synchronous socket. And so that notification is not consuming any resources, but rather whenever data is available, you get a notification, and then you can handle that data and read it out of the socket. This requires slightly different structure of the program. You have to use polling functions. We're not going to be discussing polling functions in this presentation. But you get you can get considerable performance gains if you have a lot of open file descriptors, such as, for example, a web server that has a lot of open sockets. The next flag we're going to look at is the close_exec flag, and this flag specifies whether we want to close the file descriptor whenever we start another process, or whenever we clone the process. For example, we can do a fork, and then we can call the exec call in order to replace our existing program with a new program that we load from disk. And if we want to guarantee that that all file descriptors are closed before that happens, then we have to set this flag. Because if we don't set this flag, then the file descriptors are going to be inherited by the child process. And in some cases, this can be a security risk. If, for example, you have a file descriptor open for some password file, and then you have the process execute. For example, if you have an init, a very simple example, if you have the init process that is the root process of all other processes, if that process opens some file and then it clones itself by calling fork, and then it replaces itself with another program, we don't want to have that program inherit the file descriptors that init has been opening and modifying and reading or writing, because that would be a security risk if we would do that. So we use close_exec option in order to ensure that the system will automatically close this file descriptor whenever another program is being executed. And it's important to note that this provides an atomic behavior that does not leak file descriptors. So if, for example, a leak can happen if one thread calls fork plus exec, while another, or right after another thread has called open, but before that other thread calls fcntl to set close_exec option. If we pass this option to open, then close_exec option is set in open, and that is atomic operation in with respect to executing another process. And so then it's always guaranteed to close that file descriptor if we execute another process. We also have the creation flag, and this flag specifies whether we want to create the path name if it doesn't already exist. The file is created empty, and the program must specify mode argument when using ocreate. If you don't specify the mode argument, then you can never be sure what permissions the file is going to have. That's not guaranteed, so you have to always specify the mode, which in this case would be the permissions of the newly created file. And if you do that, then you get guaranteed permissions set to whatever value you specify. We have direct access. This allows us to bypass the buffer cache. So normally when you write or read data to and from files in Linux, the data that you're reading and writing is stored in the kernel in the buffer cache. And so this considerably improves the performance of file I/O, because you can store the data in memory. And so read and write becomes very quick, and it doesn't synchronize the data with the disk that often, but instead you basically read and write RAM memory. And that is really quick. But in some cases, for example, if you have a database, you would want to have synchronization to disk to avoid data corruption, and just to make sure that all the data is synchronized with the storage where it can be read later, basically with persistent storage if you're using a disk. And for that, you can use the ODirect option, which guarantees that, but it also has it has a potential to considerably slow down I/O, because now you have to be synchronizing everything with the disk. The actual write to the disk, to the actual platters of the disk, it's not guaranteed. Only writing to the disk cache is guaranteed by this option. And you have to use the GNU source feature. You have to enable it in your compiler as a define before including fcntl in order for this option to be enabled. Now, there's several options actually in Linux, some of them are equivalent and some of them work a little bit differently. If you really want to have more detail about these options, you should check out the manual page for open call, where they are described in detail. Linux actually implements it a little bit in a little bit non-standard way. And there are small details that are important to know with the different synchronization options. We'll discuss some of these details in this presentation, but if you want to really get deep into it, then check out the man page for the open call, and they're described in detail there. We have also an option called O directory, and this will make the open call return an error if path is the directory. This is specifically added for the open diff functionality, and it's only available also if you specify the GNU source option or define globally. Then this flag will be available. We have DSync, and we also have Fsync. These two are similar in nature, but they differ. In terms of what metadata is flushed to disk when we specify one of these flags. So this flag allows us to perform writes according to requirements of synchronous data and integrity completion. So when we specify this, the DSync flag, it guarantees that the data is synchronized. It doesn't synchronize all the metadata, which means, for example, things like access time to a file. But it guarantees synchronization of data. So when you call write, the system call write is not going to return before data has been written to the disk hardware. Now, it doesn't guarantee writing to the actual disk itself, but rather transferring the data to the disk hardware, and the disk then writes that data to the actual non-volatile storage. But usually that happens really quickly, and really from the perspective of the application, it means that if some other application on the same system tries to read the data, it's going to be reading the data from the disk and from the disk cache. So to any software that is running that is accessing the disk is going to look exactly like as though the data has been stored on the disk, and very shortly the disk will write the data to the non-volatile storage. It's just that we have to remember that we're not 100% guaranteed that the data is written, but the chances are more like 99% that it's been actually stored on the disk. This forces only the metadata required to retrieve the data to be flushed to disk hardware before write returns. So it guarantees that if the power goes, then most probably the data has been written to disk, and we can safely retrieve the data back from the disk when the power is returned and when the system starts again. But we may not have the metadata saved. So we may have still old access time and some insignificant data that is not really significant for data integrity. Now, this has a significant performance impact. It can be in order of 1,000 times slower than just reading and writing from the buffer cache in the kernel. But sometimes it's useful because it guarantees integrity of the data. It guarantees that data has been flushed to the hardware. And in the case of, for example, flash disks or any kind of chips that store the data directly, we can actually be 100% sure that the data has been actually stored in the storage medium when we use this flag. We also have an option to open a file exclusively, and if we specify this flag or exclusive, then it indicates that if the file already exists, it should not be opened or created. So instead, open should fail with error set to exist, and this ensures that the caller is the actual process that is creating the file. So if you have multiple applications that need to make sure that they only create a file once, then this flag guarantees that they will not create the file at the same time. So it guarantees that there is no race condition in terms of creating the file. And this is important, for example, if you use log files. So if you want to ensure that you have only one instance of an application running on a system, then you have to use this flag in order to ensure that two applications or two instances of the same program cannot be started at the same time and still think that they are the only instance of the program running on the system. If you use O exclusive, then you have this creation of the file. The check for existence and creation of the file are performed atomically, so you cannot have two applications do the same thing and create the file twice. And to actually think that they've created the file, that they are the only owner or the first creator of the file. And we always use this flag when we want to avoid that kind of race when it comes to exclusive creation of a file. The large file option is only used on 32-bit systems. It has no effect on 64-bit systems, so we don't really need to worry about it. No A time, or actually, I mean, this flag can be useful if you're using a 32-bit system and you want to deal with large files. But on smaller embedded systems that are not 64-bit, you don't have that large files that are larger than a few gigabytes. So we don't need to use that option. But if you are curious about this option, you can check the manual pages on exactly how it works. No A time is, as I said, it's important for cases where you need to read a lot of files. And for example, when you're doing backups, you read a lot of files. That's a typical use case. You read a lot of files and you need to copy them somewhere else. But reading a file normally updates the access time to the file. So reading a file actually involves a small write operation that updates the time. And if you're reading a lot of files, you don't want that to happen. You want to you want to just read the file and not have any write operations, seek to another position on the disk, and then update that access time to the file. So naturally we can specify this no A time in order to avoid that, and this significantly improves the performance of copying a large number of files when we, for example, want to back up a large number of files in Linux. Next is the Nofollow. It basically means that we don't follow symbolic links. If we specify this option, then we get an error if we try to follow, if we try to open a symbolic link and it's actually a symbolic link and not a regular file. No block is if the file cannot be opened immediately, then open returns with an error instead of blocking. This basically it's true for FIFOs. With regular files, usually you can open the file, but if you have a FIFO, you can actually have the open call put the process to sleep indefinitely until the queue is ready to be opened. And if you don't want that to happen, you should use the non-block flag in order to prevent that from happening. So non-block basically specifies that if a system call cannot be completed right away, then it should return E again, or E would block. And these two are equivalent on Linux, but they may not be equivalent on other Unix implementations. We can also, this can be used on devices, FIFOs or sockets, and it works exactly the same way because Linux treats all of these as as files, basically. It's ignored on regular files unless you have mandatory file locking employed. We're not going to be discussing that in this presentation. Synchronization. This is similar to DSync, but this synchronizes all of the metadata. So this also synchronizes the access time in all the metadata. This is not necessarily significant for data integrity. So this is a little bit more. This does a little bit more than the DSync option. And we can also achieve the same thing by calling write and then calling Fsync. But when we use options like this, we are doing that atomically, which is important to avoid any kind of data race. Truncation. If we specify truncation, otruncate, otrunc option, then if the file already exists, then it's opened and its data is discarded, so its length is essentially 0. And we can start writing to the file from the beginning. It obviously requires write permission to the file. If you don't have write permission, you cannot use this option and be able to write to the file. Now, open does return errors. Or actually, open returns -1 if it encounters an error, and it stores the error in the errno variable, which is a global variable accessible to your application, which you can check if you get -1 returned by open. And the most common errors are permission denied, e-access. E-is-dir is if you're trying to open a directory and you're trying to open it for writing. You're not allowed to write to directories, but you can open directories for reading. That's sometimes useful. But if you specify that you want to open it for writing, you get this error. Em-file signifies that process limit for number of open files has been reached. N-file is similar, but instead for the system-wide limit of open files. If you reach the system-wide limit of open files, you get en-file. Enoent is returned whenever you call open without ocreate, and the file doesn't exist, so there is no file to be opened. ROFS is returned if the file system is read-only. For example, if you use squashfs on embedded system, you have a read-only file system at all times. You cannot write files on that file system. You have to use an overlay. eTextBusy is returned if you are trying to open a file for writing, which is currently executing. So it's a program file and it's currently executing. So you get TextBusy. These are only a few errors. If you wanna know about all the errors, you can check the man page for the open system call. There's literally a lot of them. Now, reading files. So we have opened a file and now we want to do some operations on it. And because this is a unified input-output model, we can basically read and write the file. That's the basic input-output, right? So we use the read call, and the read call is defined in unistd.h file. So we need to include that into our application if you want to use it. And it returns the number of bytes that has been read, or it returns 0 if you're trying to read at the end of file. Now, it can return less than the number of bytes you specified, and there's a variety of reasons for that. You can have, for example, if you're reading from a UART, you will get the number of bytes that would actually depend on the terminal settings you've configured, but you will get the number of bytes that are available for reading. If you're reading at the end of file, you will get the number of bytes you are able to read from the file, but not anything else because you reached the end of file. So it can return less, and it often does return less. So you have to always check for the return value and make sure that you've read the number of bytes that you've intended to read. And write works very similarly, but it instead writes the data to the file. So you specify the maximum number of bytes you want to write. You get as a return value the number of bytes that have actually been written. And it's important to remember here that when you're writing, you're actually writing to the buffer cache by default. So you're not actually writing to disk when you call write, but instead you're writing to the memory cache, which is stored in the memory. And there is a kernel thread that takes care of writing the data to the disk. So the actual writes to the disk are optimized and they happen at a later point in time. So when you're writing something, you're not actually directly writing it to the hardware. And you can if you use printf, for example, you can there's actually multiple levels of buffering. There's also buffering in the C library. So now we're talking about the direct system calls, which directly interface with the kernel. But if you use fwrite, for example, a function that is defined in the C library, it's going to use its own buffering. So if you use fwrite and you call fwrite first and then you call write, then you will actually get the result that the data you've written using write is going to write first before fwrite, because that doesn't use the higher level of buffering. So buffering is important unless we use the synchronized model where we directly write to the actual hardware. And if we use that, then we are guaranteed that the data has been sent to hardware. But it's slower as a contrary point. It's slower, and it's actually can be thousands of times slower because it's much faster to write to the memory. So you always check the return value. You check whether you've written all the data, and once you've written all the data, you know it's in cache and it's going to be scheduled for writing to the disk or whatever device you're interacting with. Yeah, and just worth mentioning, you can use Fsync and DSync. I haven't mentioned those calls. They are that will be a good topic for a separate video where we just dive deeper into the underlying logic of I/O and how all of this buffering works. When we are done with the file descriptor, it's a good idea to close the file descriptor. It doesn't always succeed. It can fail if, for example, you are writing to a network file system and it's impossible to synchronize the data. And if it's impossible to synchronize the buffers with the actual file, then the error is propagated to close and you get an error returned by close. So it doesn't always succeed. So check the return value of close and make sure that it succeeded. When we want to move around in the file, so we have our file descriptor, which is local to our process. When we want to move around in the file, we use lseek, and we can seek to a position in the file, and we can specify from where we want to seek. So we have three different options to specify. We can seek from the start of the file, which means that the offset can only be positive. And we seek as from the reference, as the reference is set to the start of the file. We can seek from the current position of the file. So if we specify seek cur and we specify 1, then we seek to the next position based on the current position of the file. And we can also specify -1, which means we go back in the file and specify and sort of go relative to the current position. And we can also specify seek end, and that puts the cursor in the file to the byte that is past the end of the file. So when we call write, if we seek end and specify 0 as the offset, then we call write, then we're going to be writing at the end of the file. Seeking can also seek past the end of the file. So we can actually seek to a position anywhere. Like we can seek many bytes or kilobytes or megabytes past the end of the file. And Linux supports this as a concept of holes in the file. So if you do that, you're not actually writing data to disk. So any data that has not been written, that is part of this hole in the file, it's not actually taking up any space on the disk. But it's like all file systems don't support that, especially Windows file systems. They don't support that kind of useful things like like having holes in the file. So instead they write zeros to the file, and so you can get like a really huge file when you don't really need to have a huge file, but you want to have a hole in the file. But this concept is not known by many people because it's kind of useful sometimes, and it's good to know. It's like when you first learn about this concept, you're like, wow, that really makes a lot of sense. But all file systems don't support this, so use it only when you are interacting with a Linux file system. Next is, and the last call that we're going to discuss here is the catch-all IOCTL, and this is used for anything that's not part that cannot be expressed in terms of like the generic IO model of read-write to arbitrary positions in the file. And IOCTL is typically used for specific functions that are specific to a device that we're interacting with. And the requests are actually unique across the whole system. So they're defined as unique integer numbers, and they are unique for the whole system. So when we call IOCTL on a file descriptor, we can pretty much be sure that we are not specifying some other request to a device that is a completely different device, which can be disastrous if you make a mistake and you use a file descriptor that actually points to a different device. But since they are unique across the whole system, we are guaranteed that if we call it on a different file descriptor that's pointing to a different device that cannot handle the IOCTL, then it will just not handle it and return an error. And these IOCTLs, they are defined in specific header files that are specific for the devices that you're interacting with. So if you're interacting with the terminal, you will include the term IO file, which specifies the IOCTLs for the terminal devices. And then you can use things like, you can set things like baud rate and different terminal specific options using the IOCTLs. So coming up next is diving deeper into the IO model. We are going to be talking about the caching, the things that happen in the background when you're interacting with files. We're going to be going in more detail to the non-blocking IO. We're going to talk a little bit more about dealing with large files. We're going to be talking about multiple read-write operations, like when we want to do a scatter-gather read or write. And we're going to be talking about duplicating file descriptors, because you can duplicate file descriptors, and you can redirect input and output. For example, when you the basic use of this is when you are redirecting output of a program to a file, but there are other uses of it. You can use it internally in your application. So we're going to discuss that, but that is a subject for the next video. And thank you for watching this presentation. I'm an embedded consultant. I specialize on Linux and RTOS systems. If you need any additional assistance with your Linux applications, then you're free to contact me. And if you want to do that, you can send an email to info@swedishembedded.com. Thank you for watching this presentation, and I'm happy you listened all the way to the end. And I'm looking forward to seeing you in my subsequent presentations. Thanks for watching, and goodbye.